Thank you. Thank you. All right. So I don't think we went on to this slide, though, which was an example of all the stuff that we said in this slide and we started talking about. But of course, this is all review because you've already done the readings, right?
Yeah.
Yeah, I thought so. Okay. So some of you could probably come up here and talk about this just as eloquently as I can, I'm pretty sure. But I don't see any volunteers jumping up, so I'll just go ahead and launch into this thing. All right, so what this is telling you is it's showing actually a couple of things that may not have been obvious when we started talking about the 4 variable K-maps. Okay, because one of the things I did focus pretty hard on were the columns. And you might recall, hopefully you recall, that when we were, maybe it's a better slide, when we were talking about how to, there's a better slide, how to create these columns, we pointed out that we went from 0 to 1, and then we reversed 2 and 3, right? So we just didn't go 0, 1, 2, 3 like you would expect in a matrix. We instead flipped these two, 0, 1, 2, 3, because that enabled us to do what?
Something about the center.
Circle.
Align the Y's and Y's knots, the X and the X knots, right? In this case here along the columns, it was at Y's and Y knots. Because I can put the 2 Y's together, the 2 Y knots together, and then I'm looking for pairs. Remember, I'm always looking for adjacent pairs. Not just pairs, but adjacent pairs. I'm always looking for those. So by flipping these two like this, that then enabled me to align it this way. Well, let's go to another one, because that's only a 2 variable, not a 3 variable. Oh, I'm going the wrong way, no wonder. Why don't you say something? I'm so bashful. Okay, I guess not. I thought I had put in another one, I guess I took it out. Okay, so hold that thought. I'm going to come back to it here just a little bit. What I'll do is I'll just stick to the prime implicant discussion at the moment. Okay? There's 2, and recall we had 2 different definitions. We had the prime implicant, and then we had the essential prime implicant, right? Does anybody remember what the difference is with the essential prime implicant? What differentiated the essential prime implicant from the regular prime implicant? Yes?
Covers one or more movements.
Well, actually, prime implicant covers one or more.
Oh, the essential.
What's the essential? What differentiates the essential from just a regular everyday prime implicant? Yes?
It covers a square on the K-map that's not covered by any other implements.
Close. If you reword it, I think you'll probably nail it, or you're off on tangent. I'm not sure which.
Like some like squares have overlaps with like other implements, but an essential one is one that doesn't have more than one like overlap, I guess, or like.
Right, it is, or we can say it is unique.
Yeah.
Yes, that's a couple different ways you can say it. Just like he said, or you can think of it as kind of a unique prime implicant. In other words, must have, right? Okay, so when we're looking at this one here, what we're first asking ourselves is, what are the prime implicants? All of them. And we're thinking adjacent pairs, right? Adjacent pairs is important. So I have these 4, well I have these pair, I have these 4, I also have pairs, I have these 4, I have pairs, I have these 4, these 2 corners here, I have these 2 corners here, I have these 2 corners here, I have that pair, and I have some that are overlapping, right? Because some of these are in more than one set of implicants. Yes?
I'm pretty clear at reading the map, but I'm just kind of confused what you mean by adjacent pairs.
Adjacent pairs means they have to be next to each other in the squares.
Representing that they both share something in common, in this case the B in common?
Yes,
Okay.
exactly. They have to have something in common. You nailed it. How do you find something in common? In a K-map, they're adjacent. Great question. Thank you for asking. So you can see all of these different groupings, and notice there's different sizes of groupings, right? We had pairs, we had groups of 4 in this 2x2, or this 2x2, or 4 input K-map. That's my sets, okay? Now, one of the purposes, we had a couple of purposes. What was one of the big purposes of the K-map? Like the number one purpose that we talked about. Yes?
Optimizing circuits.
Optimizing our circuits. Exactly. So one of the things that we want to do, once we define all of our prime implicates, is define our essentials, right? Because if we find our essentials, identify those that are unique, because that means I'm going to cover all of the ones, and just the ones that cover all of the ones, then I'm going to minimize that set. It's going to be my optimized set of hardware to implement this function with. Because remember, a K-map is a representation of what? What is a K-map?
Truth
A
table?
Karnaugh map? What?
No? Truth table?
No.
Aw.
Oh, you're close. It's that other table.
The K table?
The K table.
Yeah,
The
table,
K-map.
Karnaugh table are the same thing.
Min-term table?
We're going to use min terms in it. After we studied the truth table, we then went to a
Oh, the other one.
Another one.
a fun table. Remember there was a
Fun.
The one
fun
with the M's, right? No?
That's in terms.
No,
No?
It's a fun table. What was that fun table?
Z table?
that's the
What?
min-term table.
Z?
No. What
Dragon
was
Ball
that
Z.
fun table?
What table?
We had the truth table, and we had another
False table.
that was fun. Function table. Fun table. Function table. I should have helped you learn this thing.
Oh my god.
And so the K-map, our Karnaugh map, is a representation of the function table, right? So there's a function. There's a function that generates these outputs given this collection of inputs. And we care about the ones that result in 1. Try to keep in mind the big picture here, right? What is it that we're looking at and studying here? This Karnaugh map, this K-map, same thing, is a representation of the function table. So we have a function, f of a, b, c, d. In this case here, generates these ones. What we're doing with these prime implicants is we're identifying those input states, those values that generate 1 of a, b, c, d in this function that have some commonality with another value. So I can minimize, right? Optimize. So using 2s and 4s, collections of 2s and 4s here in this case, I'm identifying all of my prime implicates, all of the ones that are paired up with another one, either horizontally or vertically. Then my next goal is to say, I want to have the fewest number, or the minimum number, of these prime implicates. That's my essentials. And that's what this map over here represents, okay? So it's going from here to here, trying to identify all of my essential prime implicants to minimize the amount of hardware that I need to be able to generate all of these functions. Okay, so this here, this description here, this discussion here, is to define these terms and how to find them. This is the representation capturing that. Yes?
So in the essential prime implicants, how come you chose that square in the middle 80? Like, why won't you choose 80, the right below it? It still wouldn't have any overlap, so how do you know which is essential?
Why did this one instead of this one?
Instead of, like, you could have done 82, it would have still been a square with no overlaps. So why do you choose 80 in the center?
I chose it because this is unique. There's only one collection here that captures all 4 of these, and all 4 of these are pairwise.
Yeah, but I'm saying like couldn't you do, like, just move the box in the center down one and just be A?
Oh,
D,
for
and
this
go
one
with
here
C?
where I captured these four?
Yeah, like,
Yes.
why would you choose ED over that
I
one?
could.
Okay, then it would still be right?
No, it's not right.
Okay.
Because it's not my essentials. Because I can capture these with this four, this pair, and this pair. So therefore, these two specifically can be captured with one of at least 3 different prime implicants. This one here is the only one that captures those 4. Right? Okay, prime implicants. Now, having said that, we have something kind of interesting because one of the things that you might have been thinking about when you're looking at this map is saying, okay, we're focused on these ones. We have some that are not filled in. So we're assuming those to be 0, which is correct. But there are some cases where I really don't care what the value is. I have a function. It takes 4 inputs. If it has 4 inputs, I'm going to have exactly how many unique outputs?
4.
4 inputs. I'm going to have how many unique outputs?
16.
4 to the power of 4.
What's another way to write 2? What's another way to write 4?
2 times 2?
2.
Okay? So how many unique outputs will I be able to generate? What's another way to write this? I have A, B, C, D, right, as my inputs. So if I have, I'll use an OR gate. I'll use an AND gate. I tried to try an OR. It didn't come out an OR. All right?
Is there 16 possibilities?
16 unique combinations, right? Does it sound like a hexadecimal number to you?
No.
No? How many unique combinations do I have?
16? 16?
16 is what I get, right? 0 through 9, A through F, that's 16 unique combinations, right? Okay, we don't choose these by accident, by the way. If you go back to chapter 1, and as you're doing your review for exam number 1, which includes chapter 1, remember we have 4 base systems that we care a lot about, right? One of them happens to be this hexadecimal system, which you need to know and be able to generate numbers from and do algebra with, all that kind of fun stuff. You have 16 unique combinations, 16 unique outputs, if you will, based upon these inputs. Exactly 16, 0 through F. But that's my input. That's the way my hardware is set up. We talked about in chapter 1 several different representations of numbers and characters and stuff like that from different input sets using binary, using decimal, using octal, sorry, I jumped over octal to decimal, and using hex, right? So our 4 base systems. And then based upon which one of those systems you're using, I have different numbers of bits that I'm going to use to represent each one of those unique characters that I can create to generate the one output that I want. Just kind of gotta remind you where we came from this, so we know where we're going with this, right? So in one of those representations, let's take a look at one of those representations. Everybody remember BCD? What was BCD? I'm sorry, I said that past tense. What is BCD? Binary coded decimal, right? Let's review.
Yeah.
Yeah. Binary coded. What does binary coded decimal mean?
You stop counting at 8. Something like that. No?
No.
Oh.
Close, but no. What's, yes?
So it's kind of inefficient because you have to use 4 bits, but you represent things in 0 through 9 like decimal.
Exactly, decimal. What was the set of characters in binary?
0 and
0
1.
through 9.
Binary,
0,
0 and
1.
1.
0 and 1. What are the set of characters in octal?
0 through 7.
0, 1, 2, 2, 7. Decimal,
0 through 9.
0, 1, dot, 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 9. Hex,
0 to 9 and 8
0,
through
1, dot, 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 F. Remember these fundamentals. Okay? This is the alphabet. You can think of it as the alphabet or the set for binary, octal, decimal, and hex. Okay? So if I want to represent a unique number or character for any of these number systems, I need enough bits to uniquely create all of the characters in that set. And I need enough bits that I can generate each of these unique characters in these sets. So in the case of binary, how many bits do I need to be able to represent 2 unique combinations, 0 and 1? How many bits?
3.
No,
2.
1.
What? Is it a 0 or a 1?
Because it's a 0 or 1. Exactly. 1 bit can represent 0 or 1, which is the complete alphabet for binary. I'm using these terms because some of you are going to go on to some other classes later on in your curriculum that actually comes back and reviews the alphabet for some of these numbering systems and some other net representation systems as well. Okay, so these are very specific terms I'm using here. Octal. How many bits do I need to generate all of these and the minimum number of bits I need to generate
8.
all of these?
3?
3, for several 3s. 3s, right? Because 0
1, 1, 1.
is 1, 0 is 1, right? 1 is 2, 2 is 3, 3 is 4, 4 is 5, 5 is 6, 6 is 7, and 7 is 8, right? Yeah, that's it. Obviously, if you're sitting there thinking, okay, I'm starting to run out of fingers here, how many bits do I need to generate all of the unique alphabet characters in the decimal system? 4. Now we could do, so I'm going to need another bit here, right? I'll do it with a different color. I've got colors. So I need to add another bit here, and that gets me my 0 through 7. And I realized that after 7, I ran out of bits, so I need one more finger, don't I? Or one more bit. Okay, so I added another bit here, so I could throw that one, which then throws all of these to zeros, which is how I got 8. And then I need one more to generate 9, right? Which would be 1, 0, 0, 1. That's an 8. And that's a 9. And that's my alphabet for decimal. And as a couple of you pointed out, yeah, we're wasteful here in the sense that I'm not using the full alphabet that I can uniquely create. Well, with 4 bits. But I can't generate it with 3. 5 and 6 or more would be overkill. I'd be definitely wasting bits in that sense. So I have to go to 4, but I don't want to go more than 4. So I will use 4 in my decimal system. What about hexadecimal? 4. And you're going to, it's the most efficient use of 4 bits you can get, right? Because you're going to use every combination of those 4 bits to generate the set from 0 to F. And you all know how to do that. Okay, this is important because, again, it's review for the exam. It's fundamentals for the rest of your careers. Okay, if you think you're learning this for an exam, you might as well go look for another discipline right now, because these are fundamentals for your entire career. Okay, you'll even use it in your graphics class. Those of you who think you want to go on to doing graphics programming, you'll use these in graphics too. I mean, if you think there's a discipline a study area in computer science where you don't use this, maybe web programming. If you want to go into web programming, okay, you probably won't use it, but you probably will at some point when you
What
start.
about colors?
Say again?
Colors.
Absolutely, that's where I started to go. But if you want to go beyond some editor creating your HTML for you, you're going to need to still use the numbers in different representations and be worried about big Indian and small Indian, all kinds of fun stuff like that too. But we digress. This is fundamental. This is important basics to help you with your career. Know these. Did I emphasize them enough? Okay. So the points I hope is hopefully across. So coming then back to BCD, binary coded decimal. And I know a couple of you already answered this, but I want to make sure we all understand what it is and why it's important. Is because binary coded decimal means decimal, the alphabet from 0 through 9, which is represented in binary, 4 bits, binary coding. So decimal, BCD, is decimal system encoded in a binary coded system, BCD. So anytime you see BCD, it should snap right back to you saying, oh yeah, decimal, alphabet, using binary coded, which means I need 3 bits, so it'll be 4. Okay? Where's it going with this? Oh yes, so BCD. It's important in this case here because one of the things that we're going to do with our K-map is implement BCD systems with it. Okay? In a BCD system, I know that I don't care about A, B, C, D, E, or F. I don't care. They mean nothing in a BCD system. It could be 1s, it could be 0s, I don't care. The only thing I care about is from 0 through 9. Yet, I'm using 4 bits, so my K-map is going to have 4 input lines, A, B, C, D, or W, X, Y, Z. And I'm going to care about 0 through 9, but I'm not going to care about A, B, C, D, E, or F. Okay? So that is an example. There are other examples, but that is, Jerry said, the most obvious example of don't care bits in a K-map. Okay? So we have the ability to annotate don't care with an X inside the K-map for those specific values. So if I have a function, in this case here, a function 1, 4 inputs, 4 bits, W, X, Y, Z, and it's given as W or XZ or XY, okay? What I can do there is say, oh, what are my outputs for this? This particular function will generate values larger than, or 5 and larger, values larger than 4, okay? It will generate values larger than 4. Since we know it's a BCD, we add some additional information to it. And that is, okay, if it's going to generate values larger than 4, it's gonna generate zeros for 0 through 4, and then ones for 5, 6, 7, 8, 9. Values A, B, C, D, E, F, or 10, 11, 12, 13, 14, 15, don't care. Okay? I do care about the values of 0, 1, 2, 3, 4. It better be 0. And that's what this function here will do. This function will generate zeros for 0, 1, 2, 3, 4. It'll generate ones for 5, 6, 7. Oh, that's what I was going to show you. 5, 6, 7, 8, 9. And then I set 10, 11, 12, 13, 14, 15 to don't care. Okay, see that? By the way, this is the thing that this is the map I was looking for earlier, because it illustrates something else we didn't talk about when we were talking about columns, where I took 0, 1, and I reversed 2 and 3 in my columns, so I can do this y and y not thing here. Likewise, in order to get my x and w's lined up, along with my y's and z's, I'm also going to reverse these rows. All right, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So just like I did with the rows, I'm also going to flip my second pair of columns, second set of rows, so that I can have w's, x's, and z's all paired up, so I can build these adjacencies. Okay? And that's also why I went ahead and explicitly put zeros in here. If I hadn't put zeros, they would have been implicit zeros, or implied to be zeros. But I went ahead and put them in here so it'd be very obvious. 0, 1, 2, 3, and 4 are all zeros. 5, 6, 7, 8, 9 are all ones, because that's what that function's going to generate. 10, 11, 12, 13, 14, 15, don't care. I mark them with X's. Yes?
Do we not care because we're using BCD?
Correct. I'm using this function to generate BCD. Now, having at this point been looking at purely software and not hardware, you're thinking, wait a minute, mathematically, you're going to generate unique answers, right? The problem is with hardware implementations, as we're looking at these optimized solutions, I can create some optimized solutions where it might set or clear some of these values in the hardware. And what we're saying is we don't care. If it's generating a BCD value, and I can use a NOR here instead of a 3-input AND, that's what I want to do. It's cheaper. And if it sets this bit, don't care. I don't use it. So that's one of the differences between hardware and software, where software is up to this point, has been a pure implementation of mathematics. As we go into hardware and we start working with cost functions to implement the hardware, that's where we start to do things like this, where we say, hey, if I can use another component to implement logic that will uniquely generate up to here and may randomly assign these to something else, but I can do that cheaper than something that can generate exactly this set, that's what I want to do. And that's what this optimization is all about. This optimization recognizes, by using the properties of these K-maps, it recognizes that look at those pairwise requirements, creating functions that generate exactly what I want, and then being able to ignore outputs that I don't care about, enables me to come up, when I'm drawing my prime implicants, allows me to go ahead and include them or not. It's not going to hurt to include these x's, is what I'm saying. Because if it generates a 1 or a 0, it's not going to change my value. My binary coded value is still going to come out the same, regardless of whether this bit was set when these two are set. It's not going to change it. Because the thing at the end of this function is only going to listen up to 9. nothing higher. None of those other combinations of bits, another way of saying it, will cause this hardware at the end of this function to do something different. We'll only do something different and unique for 0 through 9. Other questions? Key component that you're just going to start quickly and easily using the rest of the time you're working with this. Yes?
Is there a trade-off between choosing the cheaper component and speed and efficiency and so on?
In this case here, there is, the only difference in speed and efficiency will be in the layers, which we're not talking about here with this. We're just talking about, can I identify prime implicants? Assuming that they're all at the same layer. And in that case, no, there is no difference. Great question. Other questions? Okay, think we got it? All right, so I think I said that here, right? This is mentioned, yeah. So, rules to help us with selecting our prime implicants, okay? One of the things that we want to do is we, of course, want to minimize the overlap amongst the prime implicants. Notice something very key there that I didn't say. Well, I did say, but I implied. I said minimize the overlap, right? So it's actually saying two things. One is, yeah, pick the fewest amount with the least amount of overlaps. But it also said it's okay to have overlaps, didn't it? Right? Yeah, I did. I said that. Really, I did. Minimize the overlaps. It's not the same thing as saying do not overlap. Right? So yeah, there will be, you can have overlaps. Not a problem. But what we want to do as part of our optimization, because that's why we're using K-maps, is to minimize them. Yes?
Is it possible that the minimum solution, like that there's multiple minimum solutions?
Yes, there is. There can be multiple minimum solutions. And then whatever your decision aid happens to be, there's usually other factors that can help you. But yeah, it's at that point, one's just as good as the other.
Okay.
If it gets big enough, does this turn into sort of a traveling salesman problem?
Really jumping ahead here. What we're trying to do with these are stick to specific functions and not families of functions. So what I want to do is I would solve this like if I were doing like a G of F, which I think is where you're heading with this.
Bless you.
So if I want to build a G of F, what I will do is I will minimize my G, I will minimize my F first. Then once I come up with that minimum set, I would use that in my calculation of G of F. And that's a great example because it also shows you the layers at that point, because G of F would be another layer beyond just F. Right? For those of you who didn't follow that, one of the things you learned in your calculus class, if you haven't done that yet, is we've been talking about functions, right? But you can have a function of a function. Function, in this case, G of the function of f of x. Well, typically it's multivariable at that point, but this is the minimum set, so that's why I drew it. Okay, so you can work with equations like this, and what we just said here is that this actually denotes layers in our implementation, because I would create a K-map and some components implementing f of x. Then once I've done that, I would then come up to my next layer and define a K-map and the prime implicants for G of f of x, using the optimization that I've already done here for f of x. That's it simple. Okay? Other questions? All right. So a couple of you have been asking questions then about selections then. What's the best way to select these things, okay? And this is an example, all right? So I have this function f of a, b, c, d. I don't care what the function is at this point because all we're worried about is how do I use a k-map to optimize, right? So what I could do is I could say, just like in our previous example, I've got a grouping of 4 here. I've got a grouping of 2 here. I've got a grouping of 2 here. I've got a grouping of 2 here. 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 And then it looks like it's my full set of prime implicants. So then the question is, okay, if that's my full set, I obviously don't want that many components. I want to optimize and minimize, right? So which one of these are my prime implicants? Well, this 4 set here is prime because I can only capture this one here one way. And I also claim then that this one is because that's the only way I can claim that one. This one's got 2, this one's got 2, this is 2, this is 2, this is 2, but it can only be 2 if I select one or the other. So that's my 2 sets of prime implicants. Okay? Follow that? Good? Okay. But the thing I'm concerned about coming out of this optimization is that I cover not only the prime implicants, but not only that I cover the essential prime implicants, I'm going to start with those. But then I need to also select some additional prime implicants in order for me to capture all of the ones. Okay? So even though I have on some of these multiple ways to select ones, and some of these I can only select them one way, I'll start with those. My 2 collections of the essential prime implicants was this grouping and this grouping. Okay, so I'm going to start with that. I'll grab those 4. I'll grab this pair. Notice I already have one overlap that I've accepted, right? And that's okay. We said overlaps are okay. I went ahead and selected one because that's the only way I can grab this one here, because it has to be in an adjacent pair with somebody else. It's the only way I can grab that one. So now I have choices with the remaining 5, right? I've got my essentials, but for my remaining 5, what I want to do is I want to select the fewest numbers of groups that captures all of them, right? Fewest numbers of groups. And then I claim that simply by adding 2 more groupings, this pair here capturing those 2, and then this pair here, top and bottom, capturing those 2, I've now got the full set. Yes?
For the previous K-map, in order to complete the selection, would you have asked group the other one is?
I would have had to select, and actually this is the same example, but I'm just showing it a little bit differently. I have the same 1s and 0s here. I'm showing it just a little bit differently so we can see the unique versus the multiple selection criteria. And I could have tried some other combinations. And as a matter of fact, you probably will. I just sort of jumped to the best solution, but it's not the only solution. It just happens to be the minimal, right? I could have tried some other pairs first, and what I'm doing is I'm reducing it down to the fewest sets to capture all of them. But I'm going to start with my essentials, my essential prime implicants, because I have to have those. We said we had to have those. So I start with those, and then I start working on the, I shouldn't call them leftovers, but I guess you can see them as leftovers, right? I've got to worry about those leftovers and make sure we capture them with the fewest sets possible. And that happens to be a solution for this particular function. Does that make sense? Any questions? Yes?
Why are the top left and bottom left corner not essential?
Because I can grab this one as a pair here. So I have two ways I can grab that one. And likewise, this one here, I can grab it with this pair or this pair. Yeah. Yes.
Do they have to be in groupings of 2 or 4?
I like this question. For this size of K-man, yes.
What if you had 5 by 5?
Get there. Hold that thought for a second. It's an excellent question because we're thinking, well, wait a minute, 2s, 4s, why not 3s? Why not 1s? Why not 5s? Yes.
So you said the one on the bottom left corner was an essential because you can grab it from 2 pairs.
Yes.
What about that essential in, let's see, C naught, B, C naught B, A naught D?
That one?
2 left.
That one?
How come that one's essential if it can be grabbed by 2,
Ah,
1, 2
I like this question.
pairs?
I like this question. Anybody know why? Yes.
Well, I mean, that's not the bit that makes it essential, it's the one on the right. It's just grouped with
No. It's actually, the same question applies here that, well, okay, you're right. This one we said has to be,
No, on the very
Essential.
right.
Far right.
On the
Far
far
right?
right, it has
Yes.
one thing can.
there's only one grouping,
Same with the thing on the top.
correct. So there's only
Those
one
are the
grouping
main-
here.
Those are the most essential things.
Exactly. But he's asking, I think, a little less obvious question, right? Because if you look across the row, I have the entire row of 4 in a single grouping. I don't have a pair, I don't have a pair, I don't have a pair. I have a whole group of 4. Is this the question that you're asking? Maybe not? Okay, well, let's run with it, right? Was that the question?
I was asking why that one is marked essential if it doesn't exist in.
It's arbitrary, the line is just pointing to.
It's essential because it's part of this group. I have identified this group here, which I need to grab this one because it's the only group that this one belongs in.
What if you have a group of 2 and then a group of 4 that's overlapping those 2?
If I had a group of 2 and a group of 4, and it's really, exactly, because it's the same question as if I had a group of 2, and I had a group of 2, and I had another group of 2, why do I have this group of 4? Because another unstated rule up to this point is that I want the largest size group possible every time. So I have 4 that are adjacent. I want the largest group possible. Well, that would be all 4 in a single group. Could I create a group of 2 and 2 and 2? Yeah, but that's clearly not going to be optimal. Right? Right. It's clearly not optimal. So one of our rules that we haven't spoken about yet, but is a rule, is that my groups are going to be as large as possible. And since you asked, all of my groups are going to be some number 2 to the n, except for 0. N must be 1 or larger. Okay? So, all my groups are going to be of size 2 to the n, where n is greater than 0, and I want them as large as possible. So since I have 4 adjacent, I've got a grouping of 4. Since I have 2 adjacent, I've got a grouping of 2. Since I have 3 adjacent, that's not 2 to the n, is it? That's not a group. So I create a group of 2, and I create a group of 2. I create a group of 2, create a group of 2, I create a group of 2. And that's all my groups. And then I go through this thing about which ones are essentials. Well, there's only 2 of these that are in exactly one group. So those 2 groups, in this case it's this 4 and this 2, are my two essential prime implicants in this K-map. And then since that doesn't select all of the ones, then I go through my assessment process to determine which of my other groupings gets me all of the remaining ones with the least number of groupings. Recognizing that this must be pairwise, and there must be groupings of 2 to the n where n is greater than 0. Okay? Yes?
Can you only select groupings with 2 variables, like in a pair?
It could be 2, it could be 4, it could be 6, it could be 8. Well, in this case, it can't be 6.
6 to the power.
2 to the power of 3 is, oh, I'm sorry, you're right, 6. It is 6. You're right, can't be 6, can never be 6.
And not to be an
2,
integer.
4, 8, 16, 32, 64, 128. Yeah. Thank you. Yes.
So n has to be an integer.
Yes, and it's an integer greater than 0. All right, I think we're getting the feel of this now, right? There's a couple things we haven't mentioned yet, so we'll see if we can figure those out. But first, let's see how we deal with this with the don't cares. Remember the don't cares? We were all excited about the don't cares just a couple slides ago, right? And we understand they have a very important purpose in life, right? Well, in this particular example here, we're showing you a K-map, and we're showing you a different function, okay? In this case here, it's not really a BCD, because I do care about at least one value larger than 9, right? Oh, yeah. Yeah, I do. So, I have some other don't cares, but more importantly, I have some other don't cares in here. Okay, so what I'm going to do is I still need to go through, and first thing is to identify all of my prime essentials. All of my implicants. Okay, my prime implicants. So looking for, in this case, pairs or groupings of 4s. I'm looking for groupings of 2 and looking for groupings of 4. I just go through the same logic that we just went through in the previous example. The only thing that's different is that when I'm looking for my implicants, my prime implicants, I don't care if I include an x or not. If my grouping includes an x, it's like a wild card. For those of you who play cards, it's like a wild card. You can use it or not. It can be any value you want to. It could be a 0, it could be a 1, whatever makes your life easy, right? So if you can create a grouping, of a pair by using that wild card, if you will, the I don't care value, then you can create a pair. Okay? Now you have to create a pair because even though it's an I don't care, it still can generate a value 1. So when you're going through your prime implicants, you still identify it as a pair. You've got your 4. And this actually is kind of interesting because it now creates another kind of pairwise grouping, and that is a collection of 4 in a square. Because these are adjacent, these are adjacent, these are adjacent, these are adjacent. So I now have a grouping of 4 in that prime implicant set. Likewise, the top 2, the bottom 2 is another collection of 4. Okay? So I go ahead and include the x's when I'm calculating my prime implicants. Now when I go to calculate my essentials, of course, that still comes into play. I need to make sure I capture all of my singles, right? I have a single here, so I need to be able to capture that. So there's a prime. So there's my essential prime implicant here in this grouping of 4, right? So there's my one essential prime implicant. Everything else has 2 or more groupings. So in this function, this K-map for this function, there's one essential prime implicant, and that's this grouping. So once I've identified that grouping, then what I need to do is capture the minimum number of other groupings that collect all of my ones. Now, here's where it differs from prime implicants. Okay? And I've calculated all of my prime implicants. But now, when I'm defining the set that I need that captures all of my ones, I don't need to capture any lone wolves, any x's. I don't need to capture this x because it's not going to change the output value regardless of whether it's a 1 or a 0. The big difference between this step and that step is it's like a wild card. It could be a 1, it could be a 0, it's not going to change your outcome. Therefore, it can be in the set. If it's not in a set, and I can create fewer sets without considering this particular don't care, that gives me my optimal solution because I don't care if it's a 1 or a 0. Right? So I'll collect this set of 4. You always start off with your essential prime implicant, which is this one. Okay. Now I'm going to look for my other large ones. Like I've got this large grouping of 4. If I look at that pair and this pair, these two are already accounted for, so I don't care about that 4 in the corner, right? But the 2 at the top and the 2 at the bottom, that's a grouping of 4, so I want those. That only leaves this one. I can capture that in this pairwise here, and I've got them all. And I don't care about that, I don't care. Yes?
So it's better to overlap than to take the extra don't care? Because you could take the don't care and have no overlap.
That's an excellent question. You're absolutely right. He was looking at this just a little bit differently. He was saying, well, what about if I took this pair instead of this pair? The answer is both of those would have been perfectly fine. So in the case of a tie, I chose to pair it up with one that has to be a 1 and generates a 1 anyway, then I don't care. Only because it's a stronger reasoning. If I get this pair that triggers the solution, I've got a very strong positive outcome instead of just this one bit. Yes?
So why the grouping of 4 instead of just the 2 ones?
Because that captures this and this. If I captured just these 2, then I would still need to capture this one and this one.
Right, but instead of using 4, why not just use 2?
Because my rule of thumb is that I'm always going to start with the largest groupings I can.
Yeah. You could get rid of the x's and C.
Yes, I could get rid of the x's. Absolutely right.
And it could just be
And that would have been a correct answer. My rule is I always start with the largest groupings I can. So I have a grouping of 4. I just grab it.
So that one gets done first.
You're right, it's done first. And then I'll have to worry about just this one more 1, whereas if I grab this one, I'm still looking for, oh, I got another one. It still would have worked. It would have gotten the correct results. But since I want to approach this in the same methodical approach every single time, I'm going to start with my largest groupings first, and then work my way down. Either one would have been correct. You are less likely to make an error doing the largest groupings to the smallest. Okay? Great questions. All right. Other questions? Got it. Okay. Let's see. You want some chest work? All right. So now I have set up a set of coding these things, which is another way of saying, here's the complete set of rules. Okay. So I'm gonna do 2 things at once. One, I'm gonna walk you through the 7 rules of pairwising these things. At the same time, I'm going to show you good ways and bad ways of doing each one. All right? Yeah, there's a danger because I show you something that's wrong, and you might forget to read the label where it says wrong. Okay? So make sure you do that association when you're going through these. All right, so first off, groups may not include any cell containing a 0. We're only after the 1s. and the don't cares, which is the x's, right? You don't have to have all the x's, but it's really, really important here to say our groupings are only those ones. So this would not be a pair. That would be a pair. Clear? Clear. 2. Horizontal and vertical, not diagonal. Horizontal, vertical, not diagonal. Right? So that's not a pairwise. Those are 2 pairwise, horizontal and vertical. And for the life of me, I was trying to remember that game. There's a game you play where you can go horizontal and vertical, but you can't go diagonal. I could not remember what it was.
Checkers. No, you can't.
That was it. For some reason, I was thinking king because when you get a king, kings can go diagonal, right?
They can go anywhere.
Oh, okay.
Yeah, the runners.
It's been that long since I played it.
Oh, it's been a long time. It's certainly not shoots and letters. It's certainly.
So in the game of K-maps, it's vertical and horizontal only, no diagonals in the game of K-maps. And here's the one we were just talking about earlier, right? 2 to the n, where n is greater than 0 in an integer. Okay, so yeah, you can have a pair, yeah, you can have 4. No, you can't have odd numbers. No, you can't have 6 or 15. Yeah.
So you're confronted with
Exactly. Yeah, if you were looking at that there, you would have to have 2 groups of 2. Because there's no case. If that 0 over there was a k, if that 0 over there was an x, maybe do a grouping of 4, right? But it's not. It's a 0, so you have to have 2 of 2s.
What about one of your earlier examples where you only had 1 and 0?
1, 0?
Yeah.
Well, I don't need to count for zeros.
You only had 1, 1, and 1, 0, and you can't.
Oh. Dang it, okay, I'll fix that slide. I'll fix that example. I was trying to focus, get rid of extra information, right? I was trying to get rid of extra information, but you make a valid point, because once I get here, then you're saying, but, yes, you're absolutely right. So no zeros, but clearly, we need pairs, and any 2 to the n. Each group shall be as large as possible. Right? If I can make a group 4, I'm going to make groups of 4. If I can make them 2s, yeah, but only if I can't make them a group of 4 or 8.
In the previous slide,
16.
you had a group of 3. Why is that?
Yeah.
doing the largest group possible,
Awesome.
you should just select 4 of them, and then the other ones would just be a pair.
Oh, in this case here? So now he's come back and saying, well, I've already got these 4 accounted for, so now I'll only need to worry about these 2, right?
There wouldn't be any.
So here's the deal. Try to keep it simple. Here's the deal. We're trying to keep it simple. Largest groups possible. I don't care about overlaps. Okay? All of this is saying that we set up these proofs which show that this is a stronger relationship than this is. Okay, so when I'm actually building up the logic, if these 2 will trigger and these 4 will trigger, I'd rather have all 4 of these to trigger than just the 2, because that assures that noise or other things didn't cause this value to occur.
Can you go to your previous slide real fast?
Say again?
Can you go to your previous slide really
Previous
quick?
slide, yes.
Yeah. All right, that's all. Thank you.
Okay.
Yeah, thanks.
Yes?
You said earlier we should minimize overlap. So
Yes.
does size. Is that more important?
Size trumps minimized overlap.
All right.
Yes. Yes.
So is the goal to get the minimum amount of groupings, and a method for doing that is using the largest groupings? But really our goal is to get the least number of groupings.
our goal is really to get the least number of groupings, and the unstated thing is really the strongest relationships, the strongest bits being set to enforce the correct response. That's really what we're trying to get to here. Underlying, then again, gunning down the hardware and worried about signal levels and noise and filters and stuff like that. That's kind of behind the scenes of what these are capturing, these rules are capturing. Other questions? Okay, so that's 4, 3 to go. 5. Oh, groups may overlap. Okay, we covered that one, right? Yep. Good. Why is this not good?
Not the largest groups possible.
Not the largest groups possible. Technically, I could implement the logic with this. But because of the underlying hardware that's implementing this, we want the largest groups possible for the things I stated. But also, to help us always get the correct answer, or the highest probability of the correct answer, I'm going to use the same methods as I approach this, solving each of these problems. My optimization is to generate as large a group as possible. That's going to drive me to the fewest numbers of groups possible every time. Okay, so by saying groups may overlap, and by saying that this is a more correct solution than this, I know I said wrong, but really this is a more correct solution than this, is done for several reasons. Okay, so you just want to go ahead and start thinking that way from this point forward and saying, okay, I get it. Overlaps are okay. Large is better than small in the case of groupings. And just take that approach every single time, and you'll get a better chance of getting the right answer. And the most optimized. 6, groups may wrap around the table. We saw examples of this, right? This is a pair. That's a pair. Right? Perfectly fine. What's different on this slide than the previous slides?
And this one, you think the group grouping on like the outside cell, the one previous, you kind of just define just did like the top 4, and you used to just use the pairing of the bottom 2 ones and then the side.
Yeah. Something else though, yes.
Prior to this slide, all the ones were selected, and this slide, not all the ones were selected. And
Yeah.
Situations where you awarded to the board for me.
Right. Right? I left these 3 unselected. Something else I didn't do on this slide. What was that?
The top group.
Yeah, that's true.
There wasn't like a right and a wrong.
Duh, that's the one I was looking for. Where's the right and wrong slide? Well, there were multiples. Right? I could agree to multiples. What I was trying to show here is that, yeah, I've got my tops and bottoms, but on this one here, I meant to take those other 3 ones off. But I wanted you to jump on the fact that 1, 2, 3, 4 going left and right is one set of 4, which is better than losing a pin, which is better than a pair and a pair, right? That group of 4 would have been right, this group of 2 and that group of 2 would have been wrong. Of course, like you pointed out, that completely ignored this group of 4 up here and this lone 1 down here. Yes?
What about a group of 4 that that goes around the table but instead of through the table? Is there a precedence for that?
No. This border here is as strong as this border here, or this border here. It goes back to that slide that we showed, I think it was last lecture, the circular truth table, right? That's circular. The cylindrical truth table. Because that's what this is. It's not a truth table, of course. It's a cylindrical function table. Great important. Yes?
So we can get as fancy with that as we want to. You could say, optionally, you would put the groups of 4 that you have a bar across the top. You could do the leftmost and trash it out, you get these 3, or you could do this one and this one like that.
Actually, this one, the two things that are very obvious is I have 2 groups of 4.
Yeah,
So I would get that group of 4, and I would get this group.
yeah,
And I have these 2 cells overlapping.
yeah.
That is very clear. The only choice really is whether to pair this one with this or pair this one with this. And there is no right or wrong answer on that one. Either one would be okay. Go real fast, the last one. Fewer the better, right? Okay, you have a great weekend, and